Okay, so let's start again. Some of you are having troubles with the software, as I was expecting. That's always the case with these virtual machines. But hopefully the majority of you can run the script without any issues, right? So how many of you can run the script and at least see the plots? Okay, so that's all you need basically to start playing. So if you run the script as it is, you're gonna see, well, the viewer, if you're one of the lucky ones. And at the end, you're gonna see the three plots. Let's take a look at them. The first one is showing the joint angles. So for the last three joints, the reference trajectory, which is the dotted orange line, is constant. So there is nothing going on. But for the first three joints, we have sinusoidal trajectories of different frequencies and amplitudes. And we can see that after a while, all the trajectories basically converge to the reference ones, as we were expecting, right? You may be a bit surprised by the fact that this one takes so long to converge. It's the one that takes the longest. So we're gonna take a bit of a look at why it takes so long and why it's actually completely normal that it does so. Let's look at the second plot, joint velocities. So of course, if the position is a sinusoid, the velocity is also sinusoid. And the one thing we have more here is that I'm also plotting the velocity limits. Okay, so lower bound and upper bound of the velocities. And we can see that for this joint, we have like a violation of the joint velocity limit, because the velocity of the joint is bigger than, is smaller, is less than the lower bound. And here it's more than the upper bound. But at this point, since we are not enforcing the velocity limits in the controller, that's again normal. The controller doesn't know there are limits. The simulator doesn't know that there are limits because we are just integrating. So of course you can have violations. And well, as for the position, after a while you get a convergence. Actually, you get it faster for the velocity than for the position. And finally, here you can see the accelerations. For the accelerations, we have not two, but three curves. We have the real acceleration, the reference acceleration as before, and here we have one curve more, which is the desired acceleration, which is reference plus PD. So after convergence, we can expect that the PD feedback terms are going to be very small, and so the reference and the desired are going to be equal. And since you have converged, also the real is going to be equal to the reference. So at a certain point, the three of them should be all the same, which is what we get here. Maybe it's more interesting to look at the part of the plot where this is not the case, like by zooming here. So you see the x-axis of the six plots are all connected, so when you zoom on one, it zooms also on the other five. So you always get the real acceleration, which is equal to the desired acceleration, because basically the controller is always able to achieve the acceleration that you ask for. And why shouldn't it? I mean, there is only one task to achieve, which is the tracking the desired acceleration. So you cannot have any conflicts. That's why in this specific case, you get this match. In general, we will see later that when you start adding other tasks, such as joint velocity limits or more complicated things, these two curves may be not equal. Okay. And we see that in the beginning, the reference and the desired are different, and the difference is due to the PD feedback terms. So if you just for fun, you start lowering the feedback gains, the PD gains, you're gonna see these curves getting closer and closer together. If you increase the PD gains, instead their difference is gonna get larger. But hopefully convergence should be faster if you increase the gains. So you're gonna have a larger difference between these curves, but they're gonna get together sooner. Okay. So let's focus a bit on this joint, which is the one that takes the longest to converge. What may be surprising to see, if you go back to the position, is that in the beginning, the joint is supposed to go up, but it actually goes down. Right? That was a bit surprising for me when I first saw it. But then I thought about it. We should not think in terms of how a human would move the joint, but we should think in terms of how the mathematical problem is really asking the robot to move. So what we are doing is that we are saying that each joint should move according to its reference acceleration. So this one here, and the reference acceleration is 0 at the beginning, and it goes down, plus the PD term. So since the reference acceleration goes down, well, my velocity is going to decrease if I just follow my reference acceleration. And since everything starts with a 0 velocity, so all the joints start with 0 velocity, it's kind of normal that if I follow my reference, I'm going to start going down, which is exactly what happens here. Not immediately. In the beginning, I have a very tiny movement upward because of the PD correction term, which makes the desired acceleration positive in the beginning. But then, since the reference goes down and the PD correction term doesn't increase much, well, overall my desired acceleration becomes negative basically at this point here in time. It starts being negative, and so my velocity, after going a little bit upward, it starts going downward. And that's why I get this kind of divergence, which is not really a divergence, because in the end it converges, but it just gets a bit further away, and then it comes back to the reference. So let's try to make this violation disappear here. How can we do that? Well, we can just simply add the inequality constraints to our problem. So if you scroll up the script to the point where I define the bounds for the joint velocities, you see there are 3 lines that are commented. You comment with a sharp in Python. If you uncomment them, you can see that they create a task joint bounds, which is basically incorporating joint velocity bounds and acceleration bounds, and one day I will also implement the joint position bounds. They're not there yet. So you create the task, you set the velocity bounds, and you add the task to the formulation so that it's taken into account when creating the optimization problem. And if you do that and you rerun the script, here you have the weird motion of the robot. Here you have the joint position trajectory. You can see it's a bit different, but overall you always get convergence after a while. But what really changed is that if we take a look at the joint velocity trajectory, we can see here, 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 that the velocity reaches the bounds without exceeding them. So the joint velocity limits are now satisfied. So we're very happy. Okay.
Andrea, when you say task for this, is that in the cost function or the algebra states?
They can be both. So we haven't talked about that because I haven't talked yet about priorities and weights and this kind of stuff. But when you do add motion task, you see here there is a 0, here there is a 1. So 1, so that's the priority level. 0 is as a higher priority than 1, which means that this is going to be a constraint, this is going to be a cost, the cost function. So this cannot be violated, whereas this can be violated. So actually we should also be able to see that now, because we have the joint velocity limits, you see it here. Before we had the desired and the real were always equal, right? Now that's no longer the case, because we have another task which is actually more important because it's a constraint in the optimization problem that may be in conflict with the desired acceleration. So the desired acceleration that is computed by my PD controller is asking me to accelerate when I'm already at the, well, in this case, decelerate when I'm already at the lower bound of my velocity. So at that point, the controller basically figures out that it cannot decelerate anymore, otherwise it would violate the joint velocity lower bound. And so at that point, even if the desired acceleration is negative, the real acceleration that you get is 0. And it stays at 0 until the desired becomes positive. Okay, and that's how you achieve the satisfaction of the joint velocity limit. So you basically, every time that you see a mismatch between the real and the desired acceleration, it's where a joint velocity limit was reached. Okay, and it happens all the time, basically. Here you see it very well. Okay, so let's go back to the theory for the 15 minutes we have left. Let's talk a little bit about the limitation of joint space control, because everything we have seen so far is controlling the robot in joint space, and this gonna give us some motivation to look for a new, let's say, control paradigm, which is task space control. And once we have the task space control modeled, we're gonna again frame it as an optimization problem. So we can add inequality constraints, and then we're going to talk also about multitask control in case you don't have only one control objective, but you have several ones, and some computational aspects. So the key limitation in joint space control is that you start from the assumption that you have a joint space trajectory that you would like to track. But in practice, that's not the case, right? Typically, you're not interested in the joint space motion. Even when you're controlling a manipulator, which is kind of a simple case, you typically are interested in the configuration of the end effector. If you want to do grasping, what you care about is where is my gripper and how it is oriented with respect to the object. You don't care about the joint angles. So it's much easier to specify a desired behavior in the space of the end effector pose than in the space of the joints. So how do we deal with control in case our reference is in the end effector space? For instance, it's just the position of the end effector. Well, one simple option could be, well, I take my reference for the end effector xr, and I compute a corresponding joint space trajectory qr that basically, when executed, gives me the desired behavior of the end effector. Then once I have this qr, I can apply joint space control. So I translated the problem of controlling the end effector in the problem of controlling the joints, and then I apply joint space control. Sure, you can do that. That's basically the problem in mathematical term. You need to find QR, so reference joint trajectory, such that the forward geometry of QR is equal to XR. So the forward geometry is the function that gives you the end effector in terms of the joint angles. It's called also forward kinematics. Maybe you know it by that name. So basically you need to find somehow of pseudo inverse of this function. I say pseudo inverse because it's not a one-to-one mapping typically between joint and end effector. Typically you have a higher dimensional space in joint space than in end effector space because you have more joints than degrees of freedom of the end effector. So you have infinitely many solutions. So you have infinitely many options for this pseudo inverse function. The problem is that you need to solve this inverse geometry problem, which is a nonlinear problem with infinitely many solutions. So, I mean, it's not super complicated to solve. You can try to solve it with an off-the-shelf solver, and probably it's going to work in most cases, but it's something that takes time and you will need to code. And there is also another issue, which is that tracking this reference trajectory that you get QR would be sufficient to track the end effector trajectory, but not necessary, because the robot would reject any perturbation that is pushing it away from the reference joint trajectory, even if it's a perturbation that doesn't affect the position of the end effector. So for instance, if what I care about is the position of my arm, I can do this without changing where the bottle is, right? I meant the position of my hand, not my arm. So if I have a smart controller and I get a push here, it's going to know that it doesn't need to reject this perturbation. It can just let it go. So it's going to be more energy efficient, for instance. Or it could use this extra degree of freedom to perform other tasks. Okay. Another good reason for not doing this is that this problem here is complicated. So if you know the reference trajectory in end effector space offline, you can solve this problem offline, and then it's not a big deal. But if you get the reference trajectory online because you're doing, for instance, visual servoing, so you need to grasp an object that you see online and that is dynamic, so it moves, then you cannot solve this problem offline. You need to solve it online while you do the control. And then it becomes an issue because this is, again, non-convex problem with infinitely many solutions, so it's not something easy to solve online. So while you could do this, that's not how typically people do it. So let's see another option. The other option is to do feedback control directly in end effector space. So I introduce here this symbol nu for the, basically it's a velocity associated to the end effector. Why don't I use x dot? It's the same reason why I don't use q dot for the robot velocities. It's because if x is in Euclidean space, Well, nu is equal to x dot. That if x is in a Lie group, like it contains the orientation of a 3D body, then nu is not going to be equal to x dot, and it's because it's not going to have the same dimension and the same stuff we already discussed. So you need to accept this extra notation. So we can compute the desired acceleration of the end effector by taking the reference acceleration plus PD correction term, as we did for joint space, but now we do it for end effector space. And then how do we get this desired acceleration of the end effector? Well, we know the relationship between the end effector position and the joint angles, so we can differentiate it. We get nu, which, well, in this case, I suppose it's equal to x dot, because I'm supposing that x is simply the position of the end effector, not the orientation. X dot, which is the time derivative of fg, and by applying the chain rule, I can write it as the Jacobian of fg with respect to q times the derivative of q with respect to t, right? And if I call this Jacobian matrix J, this is just J times V. So Jacobian times joint velocity gives me the end effector velocities. So if you've taken any class on industrial robotics, you've probably seen that. But I'm not satisfied yet because we are working at the level of accelerations, not at the level of velocities here. So I need to derive another time. Well, it's easy. JV becomes JV dot plus J dot V. Okay. So this is the acceleration that I would like to get at the end effector. And this is the relationship between end effector acceleration and joint accelerations. Okay. So clearly, if I have a desired value here, what is the value of v dot that I need to assign so that I get the desired value of the end effector? Well, I simply need to invert this equation. Since typically J is not a square matrix, I cannot take the inverse. So what I do is that I take the pseudo inverse. Okay. Luckily for us, typically J is a fat matrix. So it's a matrix with more columns than rows, which means that this equation has infinitely many solutions. If it was a skinny matrix, a matrix with more rows than columns, it would mean that in general it has no solutions. So in both cases, we can take the pseudo-inverse, but the meaning is very different. In this case, the pseudo-inverse is selecting one solution, the minimum norm solution among all the existing solutions. In the other case, if we take the pseudo-inverse, we are basically selecting the value of v dot, which minimizes the difference between this and this. But in general, there is no v dot that makes the equality hold exactly. Okay. Did I lose you with this? I see your face is a bit. Give me a feedback, please. It's okay. So we can compute nu dot desired as reference plus PD feedback, and then we can map nu dot desired in joint space using Jacobian pseudo inverse. And once we have a desired joint acceleration, well, we can simply map it to joint torques by using inverse dynamics, right? So this is how we did inverse dynamics control in joint space with v dot d computed as joint reference acceleration plus PD in joint space. Now we have the reference that is not in joint space, but it's in Cartesian space. So we need an extra step, which is this one, to go from Cartesian space to joint space. by using Jacobian pseudo inverse. Okay, so to compare it with the previous approach, in both cases we are computing the joint torques using this expression, which is the inverse dynamics expression. So they are both inverse dynamics controllers. The difference is that with the first option, we were computing also the PD in joint space. So we were inverting the forward geometry function at configuration level, mapping the reference Cartesian trajectory into a reference joint trajectory. Whereas in this second option, we are doing the PD directly in an effector space, which means that we are inverting the forward geometry function at acceleration level by using the Jacobian pseudo inverse. Okay. So they are not so different from one another, but in practice we're going to use this, and this is what everybody uses in our community. So let's quickly discuss pros and cons. Why is option 2 preferred? For a number of reasons. First one, the gains are defined in Cartesian space. So you have the feedback gains that have the same size of your end effector or of your task, let's say more in general. So you can also specify a gain that is higher in a direction where you would like to have a more precise control, and a gain that is lower in a direction where you don't care so much about being accurate. You cannot do that if you're doing control in joint space. There is no pre-computation. You don't need to know in advance this trajectory in an effector space to map it to joint space and do this pre-computation. You can directly, on the fly, get the reference trajectory in task space, give it to your controller, and your controller is directly able to deal with that. Okay, so it's making somehow the life easier. The only disadvantage I could think of is that, well, the controller is a bit more complicated because you need a controller that works in task space and not in joint space, so you need the extra Jacobian pseudo inverse step, which we didn't need when doing joint space control. But it's a really small complexity increase that you need to pay for getting all of these advantages. So I think that's overall the reason why everybody is using the second option instead of the first one. So, as we saw before for joint space control, also for task space control, we can very easily reformulate this as an optimization problem. Okay, how do we do it? Well, like this. So we have the same variables we had before, the joint torques and the joint accelerations. We have the same constraints we had before, which are basically the dynamics of the system. The only thing that has changed is the cost function. When doing joint space control, here we had v dot minus v dot desired. Now what we care about is no longer the acceleration in joint space, but it's acceleration in an effector space. So we minimize the difference between the end effector acceleration, which is expressed as a linear function of the joint accelerations, and the desired end effector acceleration. Okay. So I could also write this as nu dot minus nu dot desired, because this first term here is nothing but nu dot. So in terms of the optimization problem that we need to solve, it's a very small change, Variables are the same, constraints are the same, we just modify the cost function. Any doubts on that? Okay, so here I will need to start a whole new subject, and since the time just run up, I think it's a good moment for stopping. Do you have any question before we call it a day?
Yeah, one. The shape of the Jacobian is fat when is overactuated and is skinny when is underactuated, right? Or is that?
It's not the vocabulary that we use. We typically call about redundant.
Yeah, sure. So it's fat when it's redundant.
Yeah, when the robot is redundant with respect to the task, the Jacobian is fat, which means you have infinitely many solutions to your linear system of equations.
So you minimize that.
And you have infinitely many solutions, and you if you use the Jacobian pseudo inverse, what you're doing is that you're selecting the solution with the least norm.
Yeah.
Here, actually, since we are not using explicitly the Jacobian pseudo inverse, if J is fat, this optimization problem has infinitely many solutions, and which one is chosen depends basically on the implementation details of the solver you're using. So it's not a good idea to specify it like that. And in practice, we are not going to do it exactly like that. We are going to add some other terms to the cost function so that we have a problem with a unique solution. I mean, you can simply add some regularization term penalizing the norm of V dot, for instance, and that's going to be equivalent to saying that you want to choose the solution with the least norm. So you go back to the same solution you get with the pseudo inverse. Okay, thanks.